All right, AP Chem, here is your most missed questions for review number 6. You have a couple problems in here that involve half-lives, and this is your first of them. And I want to give you a little method for this. So the focus of these multiple choice questions was kinetics, and half-lives are part of your kinetics. If you read this question, it says, if 85% of a sample of pure iodine, so we have radioactive decay, decays in 24 days, what's the half-life? Your decay reactions are going to be first-order reactions because there's only one particle involved, and one particle reactions are first order. So another way to read this is how I would solve this. If 85% of the sample decays, how much is left? Well, 100 minus 87.5 gives you 12.5 left over percent. Well, how many half-lives do I have to do to get to 12.5%? Well, let's do that. Start with 100%. A half-life, if one half-life occurs, your first half-life, we'd have 50% left. If my second half-life occurs, we get half of 50 that decays, so we have 25 left. And then a third half-life would give me half of 25, which would be 12.5 left over, 12.5%. So we need 3 half-lives to reach this point. And if 3 half-lives is 24 days, one half-life would be 24 divided by 3, and that gives us our 8. Our next one, you've got 2 diagrams up here, step 1, step 2. The particle model shows the representation of a 2-step mechanism for the destruction of ozone. And you have chlorine and oxygen here. And it asks a question about this molecule, the chlorine ClO molecule. Based on the proposed mechanism, which of the following best describes concentration of the species as the reaction occurs? Well, where does this appear? It appears right here in the slow step, and then it gets consumed in the fast step, and it doesn't appear again. This is an intermediate. And an intermediate in a chemical reaction doesn't appear at the beginning, and it doesn't appear at the end. It's created and then destroyed. And now let's look at our time here. Step 1's slow, so it's slowly producing this intermediate, and as soon as it gets produced, it goes to step 2, and step 2 is really fast. It gets consumed. So the concentration of this particle we would expect to be really low. If it's slowly being produced but quickly being consumed, the concentration should be relatively low. And that's B here. The concentration is very low for a duration of the reaction, and it would be consumed in that second step. Energy distribution profile. This is a Boltzmann's curve for the Y2 molecules as shown. The reaction X plus Y2 when it's done under certain experimental conditions. Line B represents your activation energy. Which of the following changes should be made to the graph to explain an increase in the rate of reaction if the only change is a catalyst? A catalyst lowers your activation energy. So our activation energy, if it's line B, we need to move line B to the left. And that's our answer right here. Line B will move to the left because it's larger fraction of molecules will have the minimum energy to overcome the activation energy barrier. So if we get a new activation energy here, now all these molecules on our curve to the right side of it can react. There's another response in here that I just want to mention. Curve C will broaden and line B will be moved to left. The curve C will broaden. Let me see if we have another explanation. Nope. If we heat a reaction up, curve C would broaden. So it gets a lower peak if we heat it up and a bigger distribution of molecules, something like this. And if that were to happen, we heat it up, we'd have a greater proportion of molecules on this right side of line B. Line B wouldn't move if the only thing we're doing is heating it up. And that would also increase the rate of reaction because you have more particles colliding and more particles colliding with enough energy. A 2-step reaction mechanism is proposed for the gas phase reaction. Which of the following correctly identifies both the chemical equation for step 1, so this is our mechanism, we have step 1, step 2, and the rate law for the overall reaction. Here's our overall reaction. Remember, rate laws, you can't just look at an overall reaction and write the rate law. It's not just the concentration of this and the concentration of this, each raised to the first power. You can only do that for elementary steps. So the rate law for this chemical reaction is going to depend on the slow step. It depends on this step right here. That's your rate determining step. But we don't have any information about this step. So how do we get that information? Well, step 1 and step 2 have to add up to the overall reaction. So let's identify where we have all these compounds in our steps. We need CO2 in our overall reaction. Here it is, it's on the correct side and in the correct number. So I don't need any CO2 in step 1. I already have the correct number in step 2 when I add those equations together. How about my NO? I don't see any NO in step 2. So my step 1 must have an NO molecule on the product side. So when I add them up, I get NO in my overall reaction. CO appears, and here it is. So I don't need to add that in my step 1. It's in the correct number when I add them up. NO2, where does that appear? It's on the wrong side here. So when I add these reactions together, I want to have NO2 left over. So I need to have 2 NOs, 2's up here. So if I have 2 NO2's, one of these will cancel with this one, and we'll get 1 NO2 left at the end of it. And then you'll notice there's an NO3 left over here. Where does that go? Well, it needs to be produced and consumed. This would be an intermediate. So I need to have an NO3 up here as well. And let's just check to see if this step 1 is balanced now. 2 nitrogens, 1, 2. 4 oxygens, there's 1 and there's 3 more. So it's balanced. If we add these reactions together, I'll cancel now. This will cancel with this. One of my NO2's will cancel with this. And then I'm left with an NO2, a CO on the reactant side. That's what I want for the overall reaction, an NO and a CO2 on the product side. So this is the correct step 1. And now you can write the rate law. In elementary step, you can write the rate law directly from the elementary step. Rate equals the constant K times the concentration of whatever's on the left side here, which would be NO2, and then raised to the power of its coefficient, which would be 2. So this would be a bimolecular step, and that's how we get A as our answer here. This is a great problem, and I think I can point out exactly where those of you who got this wrong mistakenly interpreted this. So you've got a chemical reaction here. It's a colored chemical reaction that goes to colorless. So over time, as the chemical reaction occurs, we get lighter and lighter color in the container, and they measure, we don't need to worry about any of these quantities, but they measure the absorbance over time for the chemical reaction. And the absorbance goes down. The reason it goes down is because we have violet turning into a colorless compound and less light gets absorbed by it. Now the question asks you, approximately how long did it take for 75% of the initial amount to react? How much do we want left over then? We want 25% left over. And I think some of you probably did this. You said 25%. You went right to this column and said, where does 25% occur? It looks like 25% occurs maybe somewhere in between these two or around 200, and you chose 200 or close to 200 for your time. What do we want? We want to know when 75% gets consumed and 25% is left over. These are not percents. This is absorbance. And so I want to know 25% of the molarity or the actual concentration of this. How does absorbance relate to molarity? Well, it's a direct relationship. So if I'm 0.62, whenever I reach 25% of 0.62, that's when I've consumed 75% of my initial amount. In other words, another way to say that, if the absorbance value were cut in half, that means half of my product was consumed. That would be 1 half-life. So half-life would be right about here at 150. And then another half-life occurred at 300. So you can see 60 divided by 2 is 30, 30 divided by 2 is 15, and that would be 25% of my original sample. And so the correct answer is 300 here. Cyclobutane goes a first-order reaction from gaseous butadiene, and at a particular temperature, the partial pressure, the reaction drops to 1/8 of its original value. What does that mean? Well, if the partial pressure drops by 1/8, Dalton's law of partial pressures says all the pressures would add up to the total pressure in the container. And so it's just the partial pressure of a single part of the chemical reaction, which is our reactant. And if it cuts to 1/8, if you cut the pressure by 1/8 and everything else is constant, then you have 1/8 of the number of moles in there. So it's saying we get 1/8 left over at the end. How do we get to 1/8? Well, if we have 1, the first half-life occurs, and now we have 1/2 of our sample, and then the second half-life occurs, and we have 1/4 of our sample, and the third half-life occurs, and we get 1/4 cut in half, which would be 1/8. So this is 3 half-lives again. 124 divided by 3 would give me the length of 1 half-life, and it's C. Another stepwise reaction, which of the following represents the overall chemical equation for the reaction and the rate law for elementary step 2? So I don't think I have my, I do have my responses in here. Let's just do the math here first, or the chemistry. How do I add steps together? You just want to cancel things that are on either side, so intermediates, HI, like this. HCl, these would combine to make 2 HCl, so my overall reaction would be 2 HCl. So I've taken care of this and this. Anything else cancels? Nope, I don't see anything else that cancels. So I have H2 on this side plus 2ICl turns into 2HCl plus I2. There's my overall reaction. The slow steps, your rate determining steps, so my rate law would be rate equals K, a constant, times my concentration of H2. You can only do this if you have an elementary step of a mechanism, times concentration of ICl. So that's what you're looking for your answer. And if we look down, let's find it. Here it is. It's D. And that's it for that particular set of review questions.